Hello everyone. So today we're going to be going over max points on a line. Initially, I thought this problem was kind of easy, but we can start with the definition. Given n points on a 2D plane, find the maximum number of points that lie on the same straight line. Like I said initially, I thought this problem was sort of easy, and the theory behind that is we could just hash the slope and the intercept of each line and then see if each point is on any specific line, and then at the end we can just return the line that has the maximum number of points that was assigned to it. But in practice, this problem is actually a little bit harder, and it stems from how we compute floating point numbers in a computer, basically. So if you remember the equation of a line, y equals mx plus b, where m is the difference in y over the difference in x, we can see that as numbers become very large, we get very, very, very similar floating point numbers. And in this case, it actually is okay, right? Because the difference occurs in the 5th position, and we definitely have 5th digit precision in floating point numbers in our computers today. But as these numbers become very, very large, still in maybe double or long range, right? We can imagine that this floating point number actually becomes an approximation, a rounding, right? And if the last digit happens to round to the same number, we can get the same slope, even though the numbers, or even though the lines are different. So for example, in this case, if we happen to stop right here, we would get the same slope. And that's actually the same concept behind a much larger number. Depending on where you stop, you may get the same slope. So we can't compute m as an actual division of two integers in this case. So we can try storing m in an exact form. And an exact form is, let's just imagine we can just store the numerator and the denominator. We don't need to reduce this fraction to a floating point number. And the way we can tell if two slopes are equal is by reducing their fractions and checking that their reduced fractions are equal. So how do we reduce a fraction? Well, we can divide both the numerator and the denominator by the GCD, as seen here. So if we compute the slopes of the blue and teal line, the blue line, I picked an arbitrary point ordering based on perhaps how they're ordered in the original array. 0.2 and 0.1 for the blue line are here, and 0.2 for the teal line and 0.1 for the teal line are there. So you can see the slopes computed here, 10 minus 0, the difference in y, over 10 minus 0, the difference in x, is 10 over 10, and then the teal line is negative 10 over negative 10. And initially we can't really compare these two numbers because they're different. But if we divide by the GCD, like I was saying, and reduce these fractions, we would get 1 over 1, and then 1 over 1. But we still need to consider the b-intercept, right? Because these two lines are parallel. They do have, in fact, have the same slope, but they don't have the same b-intercept, so they're not the same line. So we can solve for b, and basically we pick any point in the pair on the line that we're trying to determine, and that will give us a y and an x. And from there we can use the m that we computed previously. So we can solve for b in an exact form as well. The problem with reducing something like this would be we're not computing m in an exact form, or in an approximate form in a floating point, so we can't actually solve for this equation because we haven't really solved for m. M is 2 terms at this point. So we can solve for b in an exact form. So if b equals y minus mx, and m is delta y over delta x, we can multiply y by delta x over delta x, which is just 1, so we're fine to do that. And then we can combine these two terms, because they now have the same denominator, into delta xy minus delta yx over delta x. And the good thing about this problem is all of the points are integers, so we are left with an integer denominator and an integer numerator at the end. And then we can divide both the numerator and the denominator by the GCD as well. So that will give us an exact form for b and an exact form for m, and then all we have to do is hash these values and count the number of points. So if we let m equals ab and b equals cd, we can store a, b, c, d as a tuple in Python, obviously, and I'm sure there are tuple equivalents in other languages. And just a reminder, we've computed m, and this would be 1 over 1, and m2 is 1 over 1. And then b we can compute with the equation just seen. 10 times with a y value times delta x, which is on the bottom, minus the x value times delta y, which is on the top, divided by delta x. So that will give us 10 minus 10, which is 0 over 1. And then we divide the GCD, and just a small note, the GCD of 0 and n is just n. So we do the same thing for the second intercept for the teal line that we were looking at, and we can see that the b-intercept is just a different number. So we can hash these two things, even though the 1, 1 are the same, the 0, 1, and the negative 10, 1 are different. So one small caveat to this problem is that there could be multiple points on the same coordinate position. So you can see here with this plot, the green point has, well, the green coordinate has 4 points on it, and the blue coordinate has 6 points on it. So all we need to do is hash the coordinates to reflect how many points are stacked there. And then when we go to determine, if we determine that a point is on a given line, we can add the number of points on that coordinate. If we determine a coordinate is on a given line, we can add the number of points to that line's sum. And then at the end, we just return the highest sum that we've seen, and that's it. So now we can go over the code, and then I'll explain that. So first I'm going to go over the naive solution, which actually doesn't need the tuple as described earlier. In this way, we can just store a slope. And the reason is we can start out by hashing the points as normal, as described. And if the length of the points hash is 1, it means we've only found one coordinate, and we can just return the value for that coordinate. Otherwise, we can check every pair of points and compute the delta x and delta y as described. And then we can check every other point. And then we can check and see if, for that point, if the slope between that point and, let's say, the ith coordinate point here is the same as the slope between I and j. And this should make sense, because if you draw a set of 3 points, if you check the slope between the first and second, and you find it's some value, and then you check the slope between the first and third, and you find it's that same value, then you know that all 3 of those points are on the same line. So that's the logic behind this solution. And because we check every point, cross every point again, it's going to be basically n cubed. where n is the number of distinct coordinates, right? Because we're hashing the coordinates in the beginning. So we're not technically checking every single point, but in the worst case, every point is unique and we are checking every single point. So it would be n cubed. Now the optimal solution starts off the same. We hash all the points and we return immediately if we've only found one coordinate. But we go through and instead of checking, having that third kind of loop, we store the tuple as described, where we store the b-intercept as well. So we don't need to determine whether or not any given point is on another line that some other pair determined, or some other pair was computed for. All we need to do is compute every pair, see what line that pair generates by storing m and b, and then count the number of times that m and b occur by adding the number of points for that specific coordinate. So it starts off the same, right? For every coordinate ij, compute the m, delta x and delta y. And then actually there is a small edge case where if the line is vertical or horizontal, we just need to hash that line, right? Because the x vertical line may not have a b-intercept, so we shouldn't try to compute the b-intercept there. And the y-intercept obviously, or horizontal line obviously has a b-intercept. It's just the y value itself, but we don't really need to worry about that. We can just store basically a wildcard n in this case, and remember that we've seen that horizontal or vertical line. Otherwise, we compute the b value as described, where we store the exact tuple of the delta x, delta y, and then the numerator of the b and denominator of b. And then we just go through and count. If we've seen the slope, or sorry, if we have not seen it, we're going to add both the number of points for coordinate 1 and coordinate 2. If we have seen it, however, we need to be a little bit smarter about how we add points. So for any coordinate ij, it's possible that we've already seen coordinate I, as part of the same line that coordinate I and j create. So as a result, we don't want to re-add I to the same line that we just computed now. We only want to add j, right? Because if I maybe generates a line between I and m, and it's on the same line as j, we only want to add j to that. So that's what this sort of block of code does. It just checks, and then at the end we check to see if the value we just updated is greater than our current max, and at the end we return the current max. So hopefully this was clear. I've commented everything. Everything is on the GitHub, this code, the diagram that you saw, and thank you for watching. And if you have interviews coming up, make sure you try to remember what you know and don't try to cram everything in, and hopefully this problem can help you in your interviews. It's always a great feeling when you see a problem that you studied or something very similar to it. So thanks again, and good luck.